Today I'll talk to you about essentially what Mark was talking about and also show some various code snippets throughout this presentation. So moving on first for some background. So I am a developer working on the GST law analysis, which is a gravitational wave analysis to search for gravitational waves in LIGO, Virgo, Conger data, which are ground-based gravitational wave detectors. So for here, we use htcondor heavily for offline analyses. They are typically very large DAGs with a lot of different interdependencies and jobs. For typical analysis, we have about order 100,000 jobs inside a DAG. So previously, what we've done is a lot of these LIGO analysis, including GST-Law, built DAGs with this this module called pipeline.py, which is used commonly within LIGO, been used historically over the last decade or so. So some motivation is the GST-Law analysis wants to run on OSG, or the Open Science Grid, to take advantage of some opportunistic resources. Our current workflow was not really feasible for OSG submission due to several different issues. One is that it was not suited for Condor file transfer. There's a lot of heavy I/O movement, relied on a shared file system, and typically was not suited for some of the typical job runtime targets for the OSG. So some of these jobs may span from order a few seconds to even, about a day or so. So some of the goals behind this was to redesign this workflow to address both of these points and simplify and optimize where possible. And since htcondor has released a Python library for the Condor Dagman through their Python API very recently, it also gave us an opportunity to move away from pipeline.py towards these native htcondor bindings. Okay, so moving away from pipeline.py, I found that the journey has been pretty smooth. For the most part, it was pretty straightforward to build small DAGs. In particular, there's this layers API within htcondor.dags, which is a very great addition, in my opinion. However, there are a few problems which myself have encountered while trying to build our very large DAG with lots of different interdependencies. The API can be a bit low level for my liking, and it tends to be a little bit difficult to track all the variables when building these large DAGs, things like arguments and file inputs and outputs, and arbitrary connections between layers are not supported out of the box. So for example, you could do things like many-to-many and one-to-one connections between layers and other sorts of things, but very arbitrary connections. You kind of have to hack around a little bit to get things to work the way you want it to.
Hey, Patrick, one quick request. Can you elaborate about the data transfer issue that you have been facing? What is your experience, or where are things not going as well or smoothly as you would like them to be?
Yeah, so essentially the previous architecture we had before, we had some of these files which could be many gigabytes in size. We use these things called file caches, which don't implicitly rely on files, things like for file transfers, but we pass these as arguments, which may contain many, many gigabytes of files that you may want to read in, but you may only use like a small subset of that. So there's a lot of thought needed to kind of move away from that structure and move towards one in which we're trying to limit I/O bandwidth and things like that.
Okay, thank you.
Yeah, thanks. Okay, so what do I mean by a low-level API? So here I lifted this code snippet from one of the tutorials for htcondor.dags within the Condor documentation. So here you define some of these variables used within the DAG. Creating these, here it creates these earlier because you're passing them in multiple places. You create this DAG object. Then here's where the layers API comes in. You create this tile layer, with the submit description, some variables, and then you create another montage layer, which is a child of the previous layer with its own submit description. So I found this works great as long as the DAGs are pretty small, but once they get pretty big, you have a lot of files, inputs and outputs and what have you that need to be tracked across multiple layers. And you need to format these arguments between the submit description, the variables, and track inputs and output files explicitly, which at least for me, it was a little bit daunting. So what I mostly wanted were a few things. One was a programmatic way of defining these arguments so that it gets formatted into submit descriptions automatically, including arguments. If I'm specifying file inputs, it adds it to the transfer input files, etc. A view into individual nodes in a layer, I'll show you what I mean later, but essentially set arguments per job in a layer and just in a way that's a little bit nicer. And then finally, node connections based on what the data jobs needs and provides rather than done explicitly. So what I mean by that is kind of similar to approach to makefiles. I personally like makefiles for very small workflows. You define the targets, you define the input files it depends on, and it kind of just builds the internal representation of the DAG based on that. And so that was kind of the approach I was going with here. So here's an example of a code snippet that kind of does this, leveraging the core htcondor.dags library. Here importing a DAG, the DAG class, and the right DAG function, and then a few extra things to create command line arguments, and then finally these layers and nodes, which are single jobs that are part of the layer. So here we create our DAG. I can create our layer configuration, which corresponds to the executable specific requirements, like I want to request 1 CPU and 2 GB of memory. And here what I want to do is add 3 nodes to this layer, each with its own set of arguments, inputs, and outputs. So here I have 1 argument, which takes a job index, which is parameterized based on the layer. You can see on the comment over here, kind of what it looks like. A verbose option, which gets expanded out to its keyword-based argument, and then bins, which, since I'm passing a list here, it automatically creates 3 of these, which is kind of a typical pattern which I've seen in a lot of these executables, which we use in our DAGs. Finally, some inputs and outputs, which are very similar to arguments, but then it also tracks the things like files for Condor file transfer, what have you. And then after you define your nodes and your layer and add them in there, you can basically expand this and kind of put it into your layer definition. And then finally, you can write the DAG to the disk. So this exact example here, we'll create this DAG file, which creates things like the job indices, the verbose option, the bins option, links up to the subfile, and there's this extra thing called node name, which you'll see in the subfile what that refers to here. So here it creates all these, typical things which I'd want for the DAG, the executable name, the arguments which rely on these variables here. You'll notice one thing, that the input and output things here that I've defined have an extra underscore. That's because any Condor reserved variables don't exactly work for this. And so to protect against that, it automatically adds this for you. Here are the requests that I have here to have Condor file transfer enabled. It also specifically adds the transfer input files and transfer output files, and sets up things like the output and error logs, which use the node name for to have unique logs here. The difference between these two is, these could get expanded out by spaces. Transfer input and transfer output files want commas in between there, and so it kind of formats all that automatically. Now, finally, what I wanted to show here is a real world example with some of our gravitational wave workflows, which I've been designing for use for the Open Science Grid. So going from left to right, we have a set of PSD jobs, and essentially, just to give some context, the gravitational wave data that gets produced by these observatories are in the form of time series data. These PSD jobs measure the noise characteristics of the data, and it's split up by time, where N are the number of splits in time, and M has to do with different ways of parameterizing the parameter space we're looking at. So going from left to right, these PSD jobs have a many-to-one relationship to this job that computes the median from all these jobs. There are these SPD jobs, which essentially transform the input parameter space with a singular value decomposition. Then the meat of the workflow, these filtering jobs, which essentially look at the time series data and try to find gravitational waves. And then finally, these ag jobs with go ahead and take the output from those previous jobs and kind of cluster things together and group them up into smaller jobs. So a typical workflow like this, N is about roughly 10,000 seconds. We process about 1 million seconds per for a typical DAG, so that's about order 100. M is about order 1,000, so this is about 100,000 jobs here, typically. And so this is, kind of the background for this simplified architecture. This is kind of what it looks like for essentially the script that generates the DAG. I've added some syntactic sugar to make things like layer definitions easier. I cut out the actual import statements here, but this DAG class corresponds to our own internal DAG class, not necessarily the one from htcondor.dags. So here you can kind of see these DAG layers correspond to this exact architecture over here. We have these PSD jobs, which take in no input, creates a set of files. Here's the median PSD job over here, takes in the PSD jobs as inputs and creates the median PSD jobs. You can kind of see this bird's eye view where you can kind of see roughly what the architecture is, in like 10 or 15 lines, and then finally writing the DAG out. So looking at next, I'll show a couple of these layers, what they look like. Here is the median PSD layer, which defines these requirements, sets up a layer, adds nodes to them, referring to these PSD jobs, these files, and then the output files, which we then attach the DAG, and notice here that I don't explicitly define which jobs depend on this. It automatically figures out what the dependencies are based on the files and needs and requests. And then here's a more simplified layer. Here's a more complicated layer, the SVD bank layers, which have different set of requirements, different executable. It loops through at nodes here. Here's a bunch of different options. It takes in two different sets of inputs, the median PSD files, which you saw earlier, as well as file inputs that don't get generated by this DAG, but are available during the time of DAG creation. And then finally writes out these SVD files. So in summary, I've written a workflow API, which is a high-level API on htcondor.dags. I found the DAGs library to be pretty useful, but I wanted a few different things to sit on top just to make life easier for me with a programmatic way of generating command line arguments and tracking job dependencies automatically. And we're currently testing this and using this within the GCL analysis to generate DAGs to run on the OSG. So thanks everyone for listening.